We propose a generic visualization approach for convolutional neural networks. CAM and Grad-CAM are prominent visualization approaches. However, their main limitation is that they work for classification networks only. Another visualization approach is masking. Masking approaches support both classification and retrieval networks. However, masking approaches have multiple technical limitations. What is the size of the mask? How to mask? Finally, masking approaches are expensive. They require a feed-forward pass through the whole networks every time the mask changes its location. This highlights the scalability limitation to videos and medical images. Visualization approaches help interpret a neural network output. Recently, they have been used for weakly supervised object location. This reduces the cost of dataset annotation. We tackle new attention visualization challenges. We want an efficient approach that works for videos and supports retrieval networks. We formulate attention visualization as a constrained optimization problem. We leverage the unit L2 norm constraint as an attention filter to localize attention for both classification and retrieval networks. Given a pre-trained CNN, feed an input frame through a normal feed-forward pass green solid path to generate the network output logits, embedding NT(x). Then, feed the same input again but multiply the last convolutional feature map by a constrained attention filter F, orange-dashed path, to generate a new filtered output FT(x), F. Optimize the filter's weights through gradient descent to minimize the difference between NT(x) and FT(x), F. Concretely, we solve this optimization problem. This formulation works for both classification and retrieval networks. It does not require fine-tuning or certain layers like global average pooling. The main limitation of this formulation is that if the input image has multiple different classes, it is difficult to generate the heat map corresponding to each class. Thus we call this formulation class oblivious and propose another class-specific formulation. The class-specific formulation is similar to the class-oblivious formulation, but it works only for classification networks with logits. This formulation optimizes the filter to maximize the logit for a particular class while minimizing the logits for all other classes. In this image, we show the heat map for an input image with both class-oblivious and class-specific formulation. While the class-oblivious formulation generates a single heat map per image, the class-specific formulation can generate a heat map per class. L2-CAF can visualize attention in both the last and intermediate convolution layers of a classification network. The class-specific L2-CAF can localize attention for different objects in a single image. L2-CAF supports feature embedding networks as well. More qualitative results are presented at the end of this presentation. L2-CAF passes the attention visualization sanity checks. The attention map changes when the network layers are randomly initialized. This indicates a high dependency between the generated attention map and the network weights. To visualize attention efficiently, we propose the fast L2-CAF version. To generate the network outputs, NT(x) and FT(x), F, we do not actually need to go through the whole network from the beginning till the end. If we know the input to the visualization filter V(x), we can skip all the trunk network computation. This observation reduces the computational cost of L2-CAF significantly because we typically visualize attention using the final convolution layer. In standard networks, the last convolution layer is usually followed by a single fully connected layer only. For quantitative evaluation, we evaluate L2-CAF on classification networks with and without fine-tuning. While Grad-CAM and L2-CAF can visualize any network directly without fine-tuning, other approaches like CAM and ADL require fine-tuning to work. After classification networks, we evaluate the L2-CAF on retrieval networks against Grad-CAM-based approaches. First, we present quantitative evaluation on classification networks. We evaluate L2-CAF against Grad-CAM on standard classification networks. Both approaches do not require any fine-tuning and can be applied directly. L2-CAF outperforms Grad-CAM when evaluated using ImageNet validation set. L2-CAF outperforms Grad-CAM because gradient-based approaches are not optimal for visualization. It has been shown that gradient-based approaches are independent of the input image in a linear architecture. For nonlinear architecture, the problem is reduced but not eliminated. Sometimes, Grad-CAM fires for non-relevant image regions. Then, we evaluate L2-CAF against CAM and ADL approaches on CUB 200 birds and ImageNet datasets. L2-CAF achieve comparable state-of-the-art results on the CUB 200 dataset. This table shows quantitative evaluation on fine-tuned classification networks using ImageNet validation set. Again, L2-CAF achieves state-of-the-art results. We evaluate L2-CAF on retrieval networks. We developed our own baselines, due to lack of efficient baselines. To develop a baseline that works directly without fine-tuning or special requirement, we extend Grad-CAM. Grad-CAM uses gradient from classification logits to combine feature maps. The weights alpha are computed using the gradient of the output logit with respect to a particular spatial location as shown in this formulation. In retrieval network, we do not have output logits. To extend Grad-CAM for retrieval networks, we made two changes to it. First, we compute the gradient with respect to the feature embedding and not a particular logit. The second modification is to replace the ReLU with an absolute function. ReLU works for classification networks because negative gradient will have a negative impact on the corresponding logit. However, in retrieval networks, it is a common assumption to embed objects on the unit circle. Thus, the feature embedding will span both the positive and negative spaces. We support this claim quantitatively and qualitatively in our experiments. For quantitative evaluate, we leverage CUB 200 and Stanford CAR datasets. These are standard retrieval dataset and both provide bounding box annotation. The bounding box annotation are used for evaluation purpose only. We evaluate L2-CAF against both vanilla Grad-CAM and Grad-CAM-Abs. Grad-CAM-Abs significantly outperforms the vanilla Grad-CAM, but L2-CAF bring further improvements. Similar results are achieved on Stanford CAR's dataset. This qualitative evaluation compares different approaches using sample CUB bird image. Retrieval network embeds images in both the positive and negative space. Thus, vanilla Grad-CAM with a ReLU can miss the main foreground object and fire for corners. Grad-CAM-Abs mitigates this limitation and focus on the main foreground object but still fires near the corners. L2-CAF focus on the foreground objects only. These are some qualitative weakly supervised object localization results. The green and blue bounding boxes indicate the ground truth and the L2-CAF localization respectively. Now, we apply L2-CAF on a generic network with a recurrent layer. We add multiple attention filters after the convolutional layer as shown in the figure. We add a single L2-CAF filter per frame. We activate and optimize one filter at a time while deactivating the other filters. Once a filter is optimized, we move on to the next filter and so on till we visualize attention in all frames. The Honda driving dataset has no ground truth or bounding box annotation. So we can only present qualitative evaluation. L2-CAF consistently highlights road marks and spatial locations of traffic light even if no traffic lights exists. Please notice the traffic light at the top right corner. This spatial location is usually attended to, even when there is no traffic light. L2-CAF uses the L2 norm constraint. In this ablation study, we show that other constraints are possible like softmax and Gaussian constraint. This figure presents the computational cost of L2-CAF on 4 different architectures. The fast L2-CAF is 7 times slower than Grad-CAM on Google Net, but L2-CAF takes 0.3 seconds per image. Before concluding, we want to highlight some remaining challenges for attention visualization. We found that L2-CAF can be used to visualize fine-grained attention through intermediate convolutional layers. In this example, L2-CAF highlights the dog's ear, cheek, and brows. However, it is not clear which intermediate layers to use. The main limitation of L2-CAF is the computational cost. L2-CAF is an iterative approach that leverages gradient descent to converge. Accordingly, the following question becomes very important. Is there a closed-form approximation equivalent to L2-CAF? In conclusion, we present L2-CAF, a constrained optimization problem, as a generic tool for attention visualization. We will finish this presentation by sharing more qualitative evaluations.